Please help me welcome Billy Cox, Intel's GM of Cloud Platforms in the Data Center Group. Billy.
It's great to be here in Paris to talk at the Open Compute Summit. I never thought I would come to Paris to talk about hardware and software, the standards, but it absolutely makes sense. Great to be here. Got some exciting things to tell you. I think it's time to disrupt the data center. We've been building data centers, arguably a legacy way, for a very long time. The guys that you see on the screen, the people you see on the screen, would not be able to deliver those services in a legacy-style data center. They had to learn new ways to do things. They had to learn new ways to buy hardware, to build hardware, to write software, to build scale-out applications. And then we found out all these devices on the other end of the wire, they wanted to connect to these services by the billions. What a great problem to have. Generates tons of traffic, tons of storage, tons of compute. I like that at Intel. I like to generate a lot of compute. But they couldn't connect any other way, right? These services have now become, they're everywhere. How many of you are using Uber to go home from here, by the way? I need to see who my competition is for getting a car tonight. They're everywhere. These are the services that we use. They're the way we connect, and they drive traffic, but they only exist because they can scale to the demand that they need at the time that they have the demand. If they had to wait 6 months to acquire hardware or wait days to get servers provisioned, they would be out of business. They've learned to do this, and it's that growth that's driving demand. It's teaching us as an industry new ways to build data centers, new ways to design servers and racks and networks and storage. And you know what? It's also driving an immense impact on our world economies, right? In the spending on internet services alone, $450 billion US, enormous amount of spends. But to support that, the infrastructure, $120 billion US, just to build out the infrastructure to support these new scale-out, aggressive data centers. But from where we are today, we think they're going to have to make some changes, right? The world that we live in today largely is around you build it, you provision it. Even if it's virtualized, you build it, provision it, and it stays. And you don't tend to move it, right? It's why bother, right? And the compute, the network and storage that we built has been optimized for that environment, which is pretty broad, right? It covers a lot of territory, but it tends to be very focused. We also see the compute, network, and storage being focused, right? They tend to be in their silos. So if you add more compute, you may or may not know how to go make the changes in the network or the storage to support it. And in general, applications today, they simply run, right? But the reality, and we've seen from some of those that I showed earlier, that those applications want to know what the hardware is that they're running on. They know that they get benefit when they can take advantage of the underlying infrastructure. They know what the server hardware compute attributes are. Can they get accelerated encryption support? That's where they need to be, but that's not where we are in a lot of cases. And so we will argue it's time for reboot the data center. Start over, build a new model, and Intel has a long history of collaboration here with the Open Compute group, and we're in fact one of the early founders in the organization. We think this is a critical way that we can now move forward and reboot the data center. So we think there's three things we need to look at in detail. One is, how can we use silicon as a mechanism to customize the application, customize the hardware for the application that's going to be run? The second is, how can we get out of those silos, compute, network, storage, so that we can treat it differently, treat it in a form that's a lot more flexible, give ourselves some choices. The third is, I need ways to let the infrastructure know what I want. And so that as I choose my services that I buy through a service provider, I know what the kind of service is that I'm getting. So, where it makes sense, let's customize the infrastructure. Let's use orchestration and tools, and then let's find ways to optimize the infrastructure to let the application pick the infrastructure that it wants. So, okay, how do we we customize? What the heck does that mean? Well, you know, Intel for years and years has been taking what Intel calls traces of applications. And we have an amazing library of application traces where we run it, and at a very low level, we capture the operational details of that application. Then when we generate the next CPU or the one after that or the one after that, we can go run simulations and have very high confidence that we know how it will perform. So the result is the current Xeon portfolio covers an immense breadth of capabilities in the data center. But we also know that there are workloads that, well, maybe they're not so big, and they benefit from a smaller form factor, lower performance, lower power, but high performance efficiency, and so the Atom line was created. And we've also seen environments where we need extreme compute performance on a certain category of workloads, and so the Xeon Phi came about. Again, expand the capability that the same CPU architecture, but used and targeted for different workloads, can be optimized for those cases. What we're entering now is an era where we can customize those capabilities. I mean, who would have thought that you could take the silicon at this level of granularity and customize it to meet your applications? But that's exactly what we see some of the very large providers doing now, is building solutions unique to their needs. We'll touch more on that in just a moment. So for those workloads, though, that need that unique focus and performance, that is an opportunity. So really, you know, Xeon covers a very broad range. There are going to be cases where you need to optimize. And we've been doing this for quite some time. When we last updated you in November 2013, we had 15 reference designs of folks, or not reference designs, 15 designs where people had customized, we had customized silicon for them. We've since then added 20 to that, and we now have 35 custom deliveries of silicon for our customers, our partners. And this customization can be lots of different things. It can be truly silicon extensions, not many of those. It can be things like microcode or firmware extensions where we have added unique capabilities for a given partner. Quite often it is special selections out of the fab for different power, or maybe different core count and power, or maybe core count, power, and frequency combinations that are most interesting to a particular customer for their application. So it can be a variety of different things. One of the examples here that I saw recently came through was a customer had a given power limit, and so now the choice was, how do we mix cores and frequencies to get the best performance for their particular app within that envelope. Another example for a given customer was we looked at how we could select parts out of the factory that would meet a specific reliability requirement. In this case, it was a 3 to 5 year usage window, and it was their ways to optimize for that. And so those are examples of how we work with customers to optimize, but we're also very specifically aware of their particular application. And so if you're general purpose, if you're building a cloud and you're going to run a large variety of applications, Xeon is your friend, because that's what it's optimized to do. If you're willing to go very deep and very close and focused on one particular area, then we have the ability to do that. And you've seen our announcements recently where we are also extending the capability to support FPGAs. This is exciting. We know of a number of different applications where there can be a significant performance boost by being able to dedicate hardware to it. So look for more to come in that space as we extend the Xeon family to embrace FPGA. Even better news, at least from my perspective, and I'm probably only totally biased, we've been doing SoCs for quite some time, system-on-chip designs for a while. Matter of fact, we have 90 design wins to date on Atom category processors for a variety of applications: compute, storage, network, IoT-related, Internet of Things-related devices. And we're now in our third generation. As has been announced, the Intel Xeon D is now in its sampling phase, will be in production early next year, or first half of next year. And Xeon D's another breakthrough. It's amazing. You should take a look if you haven't. The performance of a Xeon, so it's a Xeon product, which means it has the Xeon performance characteristics. It has an integrated 10 gig Ethernet on the same SoC, and it's in a 45 down to 20 and even below 20 watt TDP. So this is Xeon category performance in an SoC with Ethernet at low power levels. So this is a breakthrough kind of device. We're on our third pass, so we've got some history behind us. We've been doing this for a little while, and now we're beginning to see how we can take the silicon technology, our CPU design capabilities, integrate those with our networking capabilities now, and bring in some truly amazing power and performance capabilities. But rather than me tell you about it, let me now bring up a video and show you the story from one of our customers. If you could roll the video, please.
Today, 1.3 billion people use Facebook. Our mission as part of Internet.org is to connect the next 5 billion people. That presents a tremendous amount of infrastructure challenges, and one of those challenges is actually to think about how we're going to scale all of our storage solutions, especially when you think about the fact that we have over 400 billion photos today in aggregate, with over 350 million new photos showing up every day. You can imagine with 400 billion photos that not all of those photos are accessed and viewed every day routinely. There is definitely a pretty dramatic access pattern. Why that's interesting is that we can optimize the storage infrastructure in many different dimensions because of this read pattern, this kind of drop off of what happens.
Now, when we look at that, we look at building a system that scales well, that's energy efficient, and that has the compute power required to run our data storage software. One piece of technology emerged that we thought was very interesting, which is the use of a microserver to connect the storage to our network. And really for us, that's where Intel came in, because they were developing a new series of their Atom processor called the C2000. And the C2000 is designed for microserver applications. The Intel Atom technology really, for us, stood out in this case for a couple of key reasons. First and foremost, it maintains the x86 architecture that Facebook is used to deploying in our data centers. And then number two, we found that the Intel platform brought really, best of breed energy efficiency. The power draw of the Intel Atom platform was really quite low, and that allowed us to put a microserver into our storage system without creating a really complex cooling challenge. So we partnered up with Intel and jointly developed a microserver that could fit into our storage system to provide us with that sort of new global storage platform that Facebook needs to handle our ever-growing set of storage challenges. By partnering with Facebook, Intel gains access to quite a bit of sort of scale experience and some of the perspective that Facebook brings. And then Facebook gets access to the vast resources of engineering and technologists that Intel brings to the table.
So you can see that our storage needs and our storage architecture is a critical part of the product, and we also have to never relax or never sort of say that we figured this out, because the game is constantly changing and we seem to be growing faster and faster. So if you think about the overall project, it's about 12 to 14 months end to end. So it was incredible to be able to kind of pull that off and pull it all together with the help of folks like Intel and the team at Intel.
It's a great story about how to take common technology, the C2000, and create an amazing storage device. You can see that device, by the way, out at the Intel area in the expo. It's the Honey Badger design, for those of you who track OCP names. You can see it out front. We have an example of that. That partnership, and I love the way he expressed it, that we learned some of the challenges that they have in terms of scale and can partner with them, so that as we build next generation SoCs, as we build next generation processors, we can partner with them. And we partner with a lot of folks in the industry in order to learn and find those challenges. Being on the third generation says we've incorporated a lot of those changes. You can imagine that a bunch of the learnings looking forward, not just with Facebook, but with many partners, are things that we can then bring into the portfolio and bring out. And the OCP environment, frankly, is a perfect place to take advantage of that. The systems are designed to do that, and I'll touch more on exactly what we're doing in just a moment. So we talked a little bit about silos and how we need to break them down. It's easy to say, it's really hard to go do. If you're using virtualization today, then you're probably comfortable with creating a virtual machine, maybe even moving it around. What you may not be comfortable with is letting your IT partners do it on demand, let them use a self-service portal and to go initiate workloads. Well, that's where the world goes to. And what that implies now is that under the covers, you need to have the flexibility and the agility where you can allocate compute, storage, network, and even implement security options on demand. So now this is not this isn't a trouble ticket shows up and a bunch of work happens. You need an orchestration layer to go make that happen. And we partnered with the industry. I've shown two. There's also Microsoft and other projects for which we've engaged on implementing orchestration to manage across the data center, treat the underlying infrastructure more as pools of resources, and then when the applications come in, we can match it. Now, part of bringing applications in is not just hosting them in the environment, find a server to run them on, light them up and go. It's how do you set the quality of service requirements, how do you establish availability SLAs. There's a number of other things, and an orchestration layer becomes the place where you can set the policies, if you will. Here's the kind of capabilities I want this application to have. So what that ends up saying then is, okay, I'm going to allow applications to come in. I'm going to create a definition. I'm going to put an instance of them in the infrastructure. I'm going to let it run. Well, it turns out one of the things we've learned is that we need deep telemetry from the platform, from let's call it the hardware up, looking up. How is this application performing? How is the infrastructure supporting it? And I challenge many of you today to challenge us, frankly. We have a ways to go that says, okay, my app's running, I'm in a multi-tenant cloud, I've got some performance issues. How does the infrastructure help you? How do you know? Well, I guarantee you, folks like Facebook and many others who have access to the infrastructure, they see that telemetry, they can then correlate it to application performance. And so we know, we get it. So we have a number of telemetry activities going on within Intel to give that orchestration layer not just information on problems, but how to optimize the infrastructure. We have some evidence of our work inside Intel on our engineering compute where we create workload fingerprints and have able to make significant utilization improvements simply by knowing how the applications are going to run. So orchestration becomes the place where we can allocate infrastructure as we need, but I have to feed telemetry into it for it to be effective. And here's an example of how we are taking that infrastructure and backing up in a way that only Intel can and say, do we really have the right architecture? In my last lives, I've worked for OEMs and we built servers. We had 1U, 2U, 4U servers, right? That's what we built. But there really was and I even built blade systems, and that was a partial disaggregation, if you will. But what we found was, it's really not enough. And so by working on a rack scale project, it causes you to back up and say, if you're Intel and you got access to the silicon, what would you do differently? And so what we've taken an approach is it's all a bunch of pooled resources: compute, memory, storage, network, other devices. Those all become pools of resources. Now, there's different kinds of compute. There's different kinds of memory. Today it's all DRAM, but I think we know where that's going. There's different kinds of storage. There's hot, warm, cold, high performance, far away data. And there is different kinds of networks, the local networks and span data centers and continents. Well, if those are pools, when my application comes in and if he can express to me his or her requirements in terms of latency, performance, security, and efficiency, why can't I collect those resources, those pooled elements together to create the logical server that I need? And so that's exactly what RSA is. Now, it turns out that we think there's three things that we have to achieve for RSA. One is logical pools of the disaggregated resources to come together. The second is a common way to access them, right? So today, if you want to go configure your compute network and storage, you got to use at least 3 different sets of APIs, and some of those APIs vary for each vendor. And so one of the things that Intel is thrilled to partner with HP, Dell, Emerson, and others is an initiative called Redfish. and you'll see a discussion of that tomorrow in the hardware management group meeting. That work has been contributed to the DMTF and being managed there, and that's a great sign of how we can now establish an API layer so that you don't have to have all things be unique, vendor specific. The third element is the software to make it easy and possible to compose these based upon app requirements. And part of that is the apps have got to tell us what they want, and the part of it is we have to be able to say, oh, they need a certain caliber of availability, then we need to make sure we have availability zones managed and measured so that we can meet those requirements. So this is an interesting case of Intel backups, say what do we need to have in the industry, what are the required elements, and then go design accordingly. We've got a huge ecosystem evolving behind us on the rack scale work, and these are some samples of end customers and partners that are helping us design. Notice Open Compute. We see RSA, okay, I'm biased, really biased, as a great instance of an OCP design, and we're in the early stages of showing these. There is an example of a rack scale implementation in our lab, in our showcase. I encourage you to go by and see it. This is the start of what I think is the next generation. I'm thrilled that I have the software teams working on this in my organization, and it's quite exciting. You know, a lot of times when we do new products, it's okay, do what we did last time, but just for the new product. I don't think there's a day that we don't go to work on RSA and go, uh-oh, wow, the world's never solved that problem. You know, what's the right answer? And in every case, by the way, just a little bias here, we turn toward an open answer, right? So Open Compute is the great way to embody the hardware and the management aspects, the certifications, and then we work through open source communities for a lot of the software elements of it. So it's a pretty big change, pretty big. Look for this more to come. So last, and certainly not least of the three, was how do applications tell the infrastructure what they actually want? And one of the phenomena that we observed for a while was that applications would go into a public cloud, they would start a bunch of instances, and then they would look at the instance that they got and decide if they wanted to keep it or not, and in some cases, they didn't get what they wanted, so they would turn it off. So they were effectively cherry picking, you would say that in the US, cherry picking to find the one that they want. Well, we worked with a number of partners and eventually created a program called the Intel Cloud Technology Program, powered by Intel Cloud Technology. And what it does is it gives a standardized way for you to say, this is the kind of capability I want in the underlying infrastructure, so that if your application can benefit from accelerated encryption, then you know that you can get that capability or not. So some of it has to do with performance, but some of it has to do with security. Can I get a hardware root of trust certificate for this particular platform that my application is running on? Security applications. And then there's also the workload optimization. So I need a certain size and a certain instruction set to get the efficiency. This is how I specify it. So you see the wall of logos here to show the partners that have chosen to participate in that activity. So Open Compute is a place where Intel was one of the early founders. We have chosen to embrace the open aspect of Open Compute and bring not only designs but our expertise and our experience to bear. And what that means is we participate in all of the working groups. We participate at the board level and help drive events such as this one to teach our customers and partners how to do Open Compute. So it's a part of our DNA. We've been doing work in OpenStack Linux, other projects for quite some time. We released some time ago the decathlete design, and that's being updated or refreshed now for Haswell. So go look for that. That's right around the corner. So that's another example of take what we knew was well accepted in the industry. Goldman Sachs is one of the users of the decathlete design. We refreshed that now for Haswell. You, the community, then get the benefit because it's done in an open standard way. We talked a little bit, and you saw the video on the Honey Badger. This is a case of that's a workload. Okay, it's a storage application that we then build custom silicon, if you will, in this case a standard SoC, but we target a piece of silicon to go be really good at that particular workload, and then work with you, the community, to deliver very high density, very low cost cold storage type devices, the Honey Badger. You'll see further evolutions of that. At Intel, we're also embracing Ceph and bringing it into this environment, and we'll do optimizations to make sure Ceph is well structured, and other projects, Swift and other type projects like that. We talked about the open network platforms. Intel has released the hardware to support top-of-rack switches, and you'll see us extend that as we extend our portfolio of networking products. Recently, there have been announcements of NFV ecosystems being formed in the Linux community. We've also released our open network platform, which is some software to support these kinds of standard platforms. So once you have the standard platform, you can do some pretty interesting things in software, and we've chosen to do that. I gave you a few hints on the Redfish. So for those of you who've fallen in love with IPMI, maybe I've got good news, maybe I got bad news. There's a version of that standard that was developed based upon REST protocols. So for those of us who would rather program HTTP interactions, then it's a lot friendlier to us. So effectively, the first part of Redfish looks a lot like IPMI, but done on REST. But that wasn't the big deal. The big deal was we decoupled the hardware architecture from the protocol. So in IPMI, you have to know in advance which part of the subsystem you want to go get information on. In the Redfish, the REST-based protocols, you can discover what the hardware device is and then pull the relevant data only that you want. So it's more of a modern approach to how we interface with the hardware. So please come join us tomorrow in the hardware management discussion. You'll see a lot more information there on what Redfish is and how we would actually really like to have your involvement as we work on that activity in the DMTF. All right, I think it's time for us to disrupt the data center. I think I've given you some examples of how to do it. We've been doing virtualization for a while, but we need to use orchestration. We need to use the tools that we have in front of us to go make it agile and flexible. We know that the very large providers have mastered a lot of this, and a lot of that technology is flowing into open source and open hardware. It's good to go use it. Now let's go be disruptive. If for those applications for which the broad range of performance we get on Xeon is not enough, we know how to customize silicon. We have experience selecting parts that meet those requirements and to do them in a very efficient and cost-effective way. And continue to adopt open standards-based systems, open source hardware, software, partnerships. It's great to see the OCS v2 from Microsoft. It's great to see that not only are they showing us how they did the hardware, but they're giving us the operational tools that go with it. So this is an example of, by having an ecosystem, we can go well beyond what any of us can do by ourselves. So I'd encourage you, let's go be a disruption. Thank you very much.